Okay. Good afternoon, everyone. I'm Mustafa. I'm a PhD student at the FEMTO-ST Institute in Besançon. And the work I'm going to present is concerning a high-performance cesium vapor cell atomic clock based on coherent population trapping. So this work is part of a European project that aims the development of compact atomic clocks with a fractional frequency stability close to the 10 to the minus 13 level at 1 second, and going down to the 10 to the minus 15 range at 10,000 second integration. The aim volume is a few tens of liters for total power consumption of a few tens of watts. So this is to be 10 to 100 times better than commercial iridium clocks with a similar size, and also competitive with hydrogen lasers in a reduced volume and budget. These clocks will find application in navigation, in telecommunication, in defense, and also in some lab physics. Here are shown some the current state of the art for these compact clocks that are double resonance clocks, clocks using cooled atoms, and finally clocks based on coherent population trapping. You can notice here that all of these clocks have already a short-term stability close to the 10 to the minus 13 at 1 second. And the main difference is being at higher integration times where CPT clocks performance is degraded faster than other clocks. So the goal of this presentation is to expose you the main limitations of our clock and how they have been solved or how they are intended to be solved. First, let me briefly remind you some basics of coherent population trapping. The main idea is to interrogate by optical means a microwave resonator at 9.2 gigahertz for cesium atoms. So if the two ground state levels of cesium atom are linked to a single excited state by two laser fields with the frequency difference exactly equals the hyperfine separation, then these atoms are pumped into a superposition of both ground states that are not coupled to the excited state anymore. In that so-called dark state, the cesium atoms become transparent to the incident field. So you can detect a narrow CPT resonance, like just here, that can be used as a fine frequency discriminator in CPT clocks. And because there is no need here for a microwave cavity, CPT clocks acquire high potential for compactness. Well, here's shown the experimental setup. The clock relies on a single GFB laser emitting at the cesium G1 line. It's frequency modulated using a Mach-Zehnder electro-optic modulator driven by a low noise local oscillator at 4.6 gigahertz. So the first order bands generated at the output are separated by the cesium hyperfine frequency, and they are used to perform CPT. A fraction of the beam is collected here and sent to a saturated absorption setup to stabilize the laser frequency. An acousto-optic modulator here is used to compensate the optical shift due to the presence of buffer gas in the CPT cell. It's also involved in the power stabilization, and it can eventually be used to generate light pulses in the case of a Ramsey-like interrogation. Here, a Michelson system is used to generate an optimized polarization scheme that we call push-pull optical pumping, and it was first proposed by Zhou. At the output of this setup, the beam alternates between right and left circular polarization at the clock frequency, and this is shown to greatly enhance the clock transition contrast. Well, finally, the beam is sent through the CPT cell, and the transmission is detected and is used to stabilize the local oscillator frequency on the CPT resonance. Let's focus first on the laser frequency stabilization system because it has been for a long time a limiting factor. Well, we decided to stabilize the laser frequency using a saturated absorption on an annex cesium cell with no buffer gas. A fraction of the beam makes a round trip through the cesium cell, and the transmission is detected so that we can observe a well-known saturated absorption spectrum where we can stabilize the laser frequency on the narrow Doppler-free Cs here. But in our case, the laser is modulated at half the hyperfine frequency, so that the first-order sidebands are centered on the optical transitions, whereas the carrier is far from any resonance, so that we cannot use it to do the saturated absorption while performing CPT. So what we try to do is to keep the same experiment here, but instead of sending the carrier to do the saturated absorption, we sent the output of the EOM that contains the true sidebands. And here is the result. We were surprised to see that the Doppler-free dips were reversed compared to the usual case, and they also seemed much deeper. And it's even clearer on this figure where we represented the signal height over the line width of the Doppler-free dips for both configurations. And we clearly see here that the laser frequency discriminator slope is much higher in the case of a dual frequency saturated absorption. We pushed the investigation further by monitoring the bit node frequency between two independent lasers, frequency stabilized using the same kind of setup. And again, we gained 1 order of magnitude in the frequency stability when using a bichromatic field to make the saturated absorption. The complete interpretation of the physical phenomenon here appears to be rather complex, but I will try to give you a simplified overview of what happens. Suppose that the cesium atoms see two bichromatic and orthogonally polarized counter-propagating waves. The incoming wave is polarized along the x-axis, and it pumps the atoms in a dark state that we label X. It's represented here in light blue. Suppose now that the counter-propagating wave is orthogonally polarized. So it pumps the atoms in a different superposition of the same ground states here that we label Y in green. And it appears that these two states are orthogonal, so that a dark state for a linearly polarized wave is bright for the orthogonally polarized one. Well, if we now suppose that the laser fields are slightly detuned from optical resonance, then the cesium atoms can be resonant with at most one of the beams, either the incoming or the outgoing. So they can be pumped into either the dark state X or the dark state Y. But if now the laser fields are exactly at resonance, then the new excited atoms are resonant with both fields at the same time. So for these particular cesium atoms that move perpendicularly to the beam's propagation axis, the dark states are lifted and the absorption is increased. Well, this has been done for a single possible pair of Zeeman state, but of course one has to consider all possible combinations of Zeeman state, whether they're coming from the same sublevel, the hyperfine sublevel, or coming from different hyperfine sublevels. And that's why I told you it was rather complex. And still this work is under progress, and it's thanks to Emeric de Clercq from the CIRT, and thanks to Alexei Taichenachev and his team from Russia that who kindly accepted to contribute to this work. Maybe I'll skip on this, but these were some experiments we did to verify this assumption, and now we feel pretty confident with this interpretation, thanks to these results. Well, let's get back to CPT now. A spectroscopic study has been performed, and it shows an optimal CPT resonance for a cell temperature of about 33 degrees and a laser power of around 200 microwatts. Here's the typical CPT clock signal that we can detect, and it shows a contrast of 20% and the line width of 330 hertz. The expected short-term frequency stability is 2 × 10⁻13 at 1 second, according to the CPT characteristics and to the photodetector noise level. Well, here's a measurement of the short-term frequency stability that agrees with the 2 × 10⁻13 at 1 second. And what's limiting actually is the laser frequency and amplitude noise. But nevertheless, the short-term frequency stability is still comparable to the best vapor cell clocks in, that's it. At higher integration times, the clock stability is limited by the fluctuation of the physical parameters, such as cell temperature or the magnetic field. So we evaluated the impact of each of these parameters to the clock stability by monitoring their fluctuations and by measuring the clock sensitivity to each of them. For example, for the cell temperature, the sensitivity to the cell temperature is 2.53 Hertz per degree. So we evaluated the contribution to the clock stability to 3 × 10⁻14 at 1,000 seconds integration. So this is pretty high, but we expect to improve this soon by using a new cell with an optimized buffer gas ratio that would cancel the clock sensitivity to cell temperature at the first order. In the same way, the Zeeman shift contribution is 5 × 10⁻16 at 1,000 seconds, and it's pretty far below the expected specifications. We did the same study for several parameters, and it appears that the main limitation to the clock stability at 1,000 seconds comes from laser power effects. And the first solution we thought about to circumvent was to try to find a parameter that could reduce the light shift effect. So to this aim, the impact of several experimental parameters on the light shift slope was studied. And here are some of the results. And the final conclusion was that no experimental condition satisfied simultaneously a zero light shift slope without degrading the short-term stability. So the remaining solution was to try to reduce, again, the laser power fluctuations. And we tried to do that by implementing a second stage of laser power stabilization to reduce the slow drifts. And here is our first measurement in dark of the clock stability when using this two-level stabilization system. We are close now to reach the 2 × 10⁻14 level, and we suppose that this is now the limitations of the collisional shift. Well, now if we figure that we cannot stabilize the laser power enough, an alternative would be to use a Ramsey-like interrogation, where the atoms interact with a sequence of optical pulses that are used both for pumping and detection. Each pulse is separated by free evolution time where atoms are isolated from light. We could benefit from several advantages. One is to detect narrow and high contrast Ramsey fringes. And the most important one is that the light shift slope in pulsed regime is reduced by a factor of 10 in our experiment. Well, to summarize, we developed a CPT-based cesium vapor cell clock working in the continuous regime and combining push-pull optical pumping for an enhanced clock signal and an original dual frequency saturated absorption setup to stabilize the laser frequency. Well, we performed detailed CPT spectroscopy and midterm stability investigations, and we measured a fractional frequency stability of 2 × 10⁻13 at 1 second, and averaging like 1 over the square root of tau for 100 seconds. The midterm performances are limited by laser power effects and cell temperature, and some solutions are going to be tested soon, including the use of a new cell with an optimized buffer gas mixture, and also eventually the use of a pulsed interrogation. Thank you for your attention.